Hi, this is Neil Krawitz, and this talk is on applied hashes, both perceptual and cryptographic, and how they can be incorporated into image provenance and NFT technologies. In this presentation, I'm going to cover a little about my background. Then I'll focus on perceptual hashes, cryptographic hashes, how they work, and how they are different. Finally, I'll give some examples for using them with provenance and NFTs. As I mentioned, my name is Neil Krawitz. My company, HackerFactor, focuses on research and development for networking, security, and forensics. Among other things, I write the HackerFactor blog and run the photoforensics web service for digital photo analysis. I also run a search by image service called Routabout, which uses perceptual hashes to find pictures from the Internet Archive. When people hear the word hashes, they usually think about cryptographic hashes, which are used to tell if two files are the same. Perceptual hashes are a different concept. They are used to compare based on similarity. For pictures, they can find variations of the same image, and for audio and video, they can identify similar segments or clips. To help explain these differences, I'm going to go back to the basic definition of a hash and how they relate to random numbers, cryptography, and perceptual attributes. So what is a hash? In computer science, a hash refers to any kind of binning algorithm. This is like a first-pass rough cut at sorting data. It's used to segment data by attributes. When sorting data, there is no real limit to the number of available bins. There could be dozens, hundreds, or even millions of bins for hashing or grouping the data. It really comes down to the number of desired bins and the specified binning algorithm. Sometimes you want to bin by specific attributes. However, sometimes, like with cryptographic hashes, you just want consistent groupings of data even if the groups are randomly selected. An easy way to randomly group data is to use a random number generator as the hash function. A random number generator is an algorithm that generates a sequence of unpredictable numbers. Regardless of the specific random number system, every random number generator has the same basic configuration. There's an algorithm that mixes numbers and an internal state with a number for mixing. Each time you call the random number generator, it loads the internal state and mixes up the bits. Some of the mixed bits are used for the output value, and some are used to update the internal state. A simple random number generator works great at producing a pseudo-random number sequence. However, if someone knows the algorithm and has enough output data, then they may be able to determine the internal state and predict the next output value. More complicated random number generators watch for input that is unrelated to the internal state. This could be things like keyboard timings, when packets arrive over the network, or disk I/O transfer rates. Each time this external data, or entropy, is received, it updates the internal state. This way, someone who knows the algorithm cannot predict the next random value even if they have lots of previous values. Cryptographic hash algorithms work like random number generators. Each uses a well-known mixing algorithm and a specific initial state. The data being hashed is used as external entropy and updates the internal state. After all of the data is processed, the final state generates the hash's value. There are lots of different cryptographic hash algorithms. Most differ by the complexity of the internal mixing system and the size of the final hashed output. For example, MD5 uses a relatively small mixing system and generates 128 bits or 16 bytes of output. SHA-1 is more complicated and generates a 160-bit or 20-byte hash value. And SHA-256 is even more complicated and generates a 256-bit hash value. As an example, I have a file called board-ape. Although the file extension is .img, the contents are in an image format called WebP. The file is 72K and it has a specific image size. This is not unique. You can have your own file with the same file name, format, size, and dimensions. However, I also generate some cryptographic hashes. If your file doesn't have the exact same cryptographic hashes as my file, then your file is not the same as mine. And if your file has the same cryptographic hashes, then we can be very confident that you have, byte for byte, the same file as me. With cryptographic hashes, the same input file always generates the same output sequence. If the files differ even by 1 bit, then the hashes will be different. If the hashes are the same, then they are likely bit for bit identical. With cryptographic hashes, there is no degree of similarity. They are either different or they are not. You may have noticed that I used the word likely. If two files have the same hashes, then they could be the same file. This is because hashes map large datasets into small signatures. While unlikely, it is possible for two different files to generate the same signature. When this happens, it's called a hash collision. To put this into perspective, MD5 generates a 128-bit or 16-byte hash value. An input file will map into one of these 16-byte values. This means that there is a 1 out of 2 to the 128th, or 1 in 340 undecillion, chance of having two different files with the same MD5 hash. Due to algorithmic weaknesses, it's actually more like 1 in 2 to 97th, but that's still a huge number. With odds like that, you're better off playing the lottery. MD5 is considered weak by today's standards. Other hash algorithms use more bits and more complicated algorithms for a lower chance of a collision. Perceptual hashes use a different binning concept. They don't use a random number generator. Instead, they group content based on attributes like how is the image colored, the location of colored transitions, also called gradients, or the location or orientation of edges. They can also focus on critical points or frequencies from signal analysis. These attributes can be global to the entire picture or local to specific regions in the picture. Just as there are lots of different cryptographic algorithms, there are lots of different perceptual hash algorithms. Many of these algorithms are field-specific. For example, astronomers take photos of the night sky and need some way to align similar photos of stars. One algorithm for doing this treats every star position as a critical point for alignment. As long as the stars are in the same relative positions, the images will match. Fingerprint matching uses a similar technology. The ridges define critical points for alignment. Locality-sensitive hashing is often used for matching similar text. A simple example of this is the common Unix diff program. In this example, I have two text files. One says, "This is a test of text." The other says, "This is another test of similar text." The diff program determined that the word "a" was replaced with another, and the word "similar" was inserted. Audio perceptual hashes, such as beat alignment, can be used to identify songs or audio clips. And algorithms like video barcode can be used to match video segments. For images, there are many different perceptual hashing systems, but most of them are proprietary. For example, Google's search by image system appears to be based on some kind of colored histogram and edge detection technology. Bing's image search is similar, but appears to be based on overall intensity. When I asked TinEye about their solution, they said it was magic, but it's likely based on critical point alignment. KarmaDK has indexed pictures from Reddit. They use a gradient hash system that I blogged about. My own routabout system uses a set of global intensity gradients. In contrast, PhotoDNA, which is used for identifying child pornography, uses 36 sets of localized gradients. Most perceptual hash algorithms are not very complicated. For example, average hash, or ahash, uses a few simple steps to create and compare hashes. First, any borders around the content are cropped out. Second, the large image is reduced to 8x8 pixels. That's really small. The small image is converted to grayscale, and the average grayscale intensity is identified. Finally, the picture is converted to black and white, which represents the 0 and 1 bit values. Each bit indicates whether each of the 8x8 pixel intensities is above or below the average value. For comparing two hashes, you just need to count the number of bit differences. To demonstrate how this works, I'm going to use three pictures. The first is a JPEG that shows Kim Jong-un holding a DVD. The second is a PNG where someone replaced the DVD with an iPhone and closed his eyes. The third picture is a Bored Ape WebP file. For generating the ahash value, we first crop the images. The Kim Jong-un pictures removed the white border at the top and the black border at the bottom. The Bored Ape removed borders from the sides and top. Then the pictures are scaled down to 8x8 pixels. This removes almost all of the details from the pictures. The small image is converted to grayscale, and then the average color is determined. The image is finally reduced to black and white based on whether the grayscale intensity is above or below the average intensity. The black and white image has 8 pixels per row, and there are 8 bits in a byte. We can directly convert each row into a bit sequence. For example, the first row is white, 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 black, black, white, white, white. That translates to bits as 11100111, which is the byte value E7. We do this conversion to each of the 8 rows. This byte sequence is the perceptual hash of the image. To compare hashes, we simply count the number of bits that changed. For example, E to F is a 1-bit change, 7 to 7 has no bit changes, and C to D is a 1-bit change. The two Kim Jong-un pictures differ by 2 out of 64 bits, or 3% of the total hash. In contrast, the Bored Ape differs from Kim Jong-un by 35 out of 64 bits, or 55% of the total hash. Now we can algorithmically determine that the two Kim Jong-un pictures are visually similar, but not identical, while the Bored Ape picture is very different. Using this, we can determine a threshold or a cutoff level to detect visually similar pictures. The A-hash perceptual hash is format independent. The file can be a JPEG, PNG, WebP, or any other kind of image format, since the algorithm looks at the rendered pixels and not the file's encoding. A-hash is also padding resistant, since any border around the image is removed. And A-hash is aspect ratio independent, since it reduces the image to 8x8 pixels regardless of the aspect ratio. One of these pictures looks very elongated, but they both have the same perceptual hash value. Because A-hash crushes the image down to 8x8 pixels and focuses on the average grayscale intensity, you can crop as much as 1/16 of the image from any edge without significantly changing the hash value. Similarly, recoloring the picture a little may change a few bits in the hash, but most of the A-hash value will remain the same. And small edits won't make large changes to the A-hash value. This makes A-hash resistant to minor edits. A-hash is an example of a very simple perceptual hash algorithm, but it works pretty well. Different pictures should have different average color intensity distributions. However, there are lots of alternative perceptual hash algorithms. For example, D-hash focuses on adjacent pixel gradients. The black-white conversion determines whether the pixel on the left is brighter or darker than the pixel on the right. With pictures, low frequencies determine structure and high frequencies provide details. P-hash and W-hash focus on the lowest frequencies in an image. Most perceptual hash algorithms are applied globally, evaluating the entire image. PhotoDNA focuses on local gradients in an overlapping grid. Another option uses scale-invariant feature transforms, or SIFT, to identify and align critical points. Even among these algorithms, there are implementation variations. For example, A-hash, D-hash, and P-hash use 8x8 pixels to create 64-bit hashes. However, they can be easily extended to use 16x16 pixels for 256-bit hashes, 24x24 pixels for 576-bit hashes, or larger. Larger hashes generally means larger resolution for edit detection. As an example, I submitted the Bored Ape picture to TinEye and immediately found 310 results. However, the results spanned a variety of Bored Ape images. TinEye focuses on features, and all of the pictures have similar base features. Fortunately, perceptual hashes permit sorting the results by similarity. When sorted by most similar, the first picture that TinEye listed was a little darker than my submission. The next pictures had similar coloring but different borders and cropping, and yet they are visually variants of the same picture. As another example, I searched for the cover of the book titled Abraham Lincoln using my Roundabout search system. Roundabout found 10 variants of the image. Some have different dimensions, and some show the same book in a different language. Roundabout associates each picture with meta information. Besides finding the different variants of the picture, you can also find each collection at the Internet Archive that contains each picture. Just as cryptographic hashes can have collisions, perceptual hashes can also have collisions. However, with perceptual hashes, the collision is not based on the number of bits. Instead, it's based on the likelihood of having similar attributes. For example, the coronavirus, a dinner plate, and the Japanese flag all appear similar under A-hash. Regardless of the perceptual hash algorithm, low-detailed images will all appear similar. Every picture of a white wall looks the same. and every picture of a UFO in the night sky looks similar. The likelihood of a perceptual hash collision is dependent on the algorithm and the threshold for determining similarity. Depending on those choices, all of these Bored Apes could be similar, or they could all be different. There are a couple of approaches for resolving collisions. First, you can use different algorithms. Different algorithms evaluate different attributes. Second, you can use different bit lengths. If the 64-bit A-hash algorithm isn't sensitive enough, then maybe try 256 bits. And third, you can adjust the threshold for determining when two pictures match. The great thing here is that you have lots of options. You can tune the perceptual hash for your specific problem space. Now that you understand how hashes work, we can start to address privacy. Hashes are often used when you don't want the server to store the actual data. As long as the hashes match, that's often enough to confirm a relationship with the source data. For example, cryptographic hashes are generated using a random mix, so they cannot be mapped back to the input data. This makes them a great option for storing passwords. As long as the entered password generates the same hash, you can assume that the user entered the correct password. And if the user's password doesn't generate the same hash, then you know that they didn't enter the correct password. If someone were to compromise the server and take the password file, then they would have hashes and not the actual passwords. In order to find the user's password, they would need to crack the hash. Brute force cracking tries every password combination, but since there are billions of combinations and computing each hash takes time, this is usually not a practical approach. Most attacks iterate through a list of common words and variant patterns, such as appending numbers or replacing certain characters. Unlike cryptographic hashes, perceptual hashes have a property called projection. With perceptual hashes, every bit represents an attribute. This means that hashes can be projected back into a picture. For example, a hash maps a small black and white picture into bits. By the same means, the bits can be easily used to recreate the black and white picture. The 256-bit version of a hash contains more bits. It can be used to project a 16 by 16 pixel image. More bits means the projected image has higher resolution. P-hash stores bits that represent the lowest frequencies in the picture. This may look like blobs to a person, but to the computer, different images result in different blobs. In general, fewer bits result in less projected resolution. You won't get a recognizable image from a hash that stores 64 or even 256 bits. In contrast, PhotoDNA uses 144 bytes to store overlapping gradient information. That's 1,152 bits, which means it can project into a much higher resolution image. A picture projected from PhotoDNA appears as a blurry, grayscale version that is 26 by 26 pixels. That's about the size of a small desktop icon, and it has enough detail to identify the picture's content. When it comes to selecting hashes, people often ask for the best. However, there is often no best choice. With cryptographic hashes, the general rule is that more bits is better. SHA-1 is longer than MD5, so SHA-1 is better than MD5. SHA-256 is longer than SHA-1, so SHA-256 is better than SHA-1, and so on. The biggest trade-off is data storage, readability, and computation speed. Longer hashes typically take more computation time, need more storage space, and are not human readable. With perceptual hashes, the general rule is that more bits provide more resolution. Depending on what you're comparing, you may not want a high-resolution hash. In addition, different hashes measure different things. Depending on the media you are indexing, you may prefer gradients over colors or frequencies instead of gradients. In general, there is no generic better. There's only better for your specific needs. Now that we know how hashes work, we can focus on how they can be used with provenance and NFT technologies. Provenance provides information about the media, such as where it came from, how it was altered, and who performed the alterations. There are different proposed implementations. In general, they include a list of identifiers, actions, claims, and digital signatures. The unique identifiers can be generated using cryptographic hashes or random values, like a universally unique identifier or UUID. The digital signatures and tamper detection codes can be generated using cryptographic hashes. Most provenance solutions attach the information to the media as metadata. However, many tools and services, including Twitter and Facebook, strip out metadata. So what happens if someone removes the metadata? If this happens, then we could use a perceptual hash to find the media's provenance information. For example, we could generate a perceptual hash from the media and provide it to a signing authority. The signer could use the perceptual hash to search all of their holdings and then return a list of similar media and provenance information. This does introduce a few problems. These include having too many options, concerns about privacy and compatibility, proprietary solutions, and a requirement for trust. For example, different signers and services handle different content. We should expect different services to use different perceptual hashes. And we cannot expect signers to generate every possible perceptual hash for all of their holdings. Will users generate the hash or download a service-specific module? It's often easier to upload the media to the service and let them generate the hash. But sharing the media brings up privacy. Sometimes you can't provide the media to the signer due to the content, legal restrictions, or a need to protect the source's identity. With all of these options, we're certain to have compatibility issues, such as which media formats are supported. For pictures, JPEG and PNG are common, but what about Apple's HEC or Android's AVIF? If you need to download the hash system, then which platforms are supported, and what are the minimum system requirements? If the algorithm is proprietary, then you can't share the hashing system with the end user. This brings up the issue of trust. If I have to download and run a hashing module, then how do I know it doesn't contain a virus or spyware? Will there be requirements for DRM or heavily obfuscated code? If I have to upload content, then the service needs to expect hostile images, such as JPEG files that intentionally crash the JPEG library. And if I have to upload, how do I know that the service won't retain my private content? The applicability to NFT services is very similar. Every NFT provider has their own complicated architecture. These are heavily dependent on cryptographic hashes for identifiers, signatures, and validation. Most are also based on blockchain technologies, which are heavily dependent on cryptographic solutions. An NFT is a pointer to some media. But how do we map the media back to an NFT entry? What if the media is converted to a different format? Then we cannot depend on cryptographic identifiers. Also, how do we find out if the media is registered at multiple NFT services, or even if it is registered at all? One solution is to use perceptual hashes. As with the provenance problem, you can generate a perceptual hash and then have the NFT service scan all of their holdings. This has the same trade-offs as before, such as which perceptual hash to use, privacy for shared media, proprietary hash algorithms, compatibility, and trust. To wrap up this talk, I provided a brief overview of cryptographic and perceptual hashes, including how they work, hash collisions, and reversibility. Finally, I showed how they are applicable to provenance and NFT technologies. Again, my name is Neil Krawitz, my company is HackerFactor, and I thank you for your time.